lipids today. And the point is that lipids are nonpolar. Okay? All of them. There are two big categories. One category of lipids contains fatty acids, like the ones I exemplified on the whiteboard earlier today. And another type contains steroid nuclei. Since they are nonpolar, they're soluble in organic solvents, but not soluble in water. And they're named after the Greek word, which means fat. So we're going to try to figure out which lipids exist and what they're important for. So as we discussed, lipids can be broadly divided to two groups: fatty acids and steroids. So waxes, fats, oils, and phospholipids are esters. You can see that this hydroxide group can form an ester with an alcohol. On the contrary to fatty acids, steroids do not contain, those long chains do not contain ester group, and therefore can be hydrolyzed, cannot be broken down. But they have this nucleus of 4 aliphatic, non-aromatic, fused carbon rings. So within the fatty acid realm, you can see that there are 4 subgroups. Triacylglycerols, we're going to talk about them. That's the energy storage, things like fat and oil. Glycerophospholipids. This is substances that form cellular membranes. Sphingolipids, also found in cell membranes, and waxes, which you encounter all the time in when you look at the plants, for example. They're covered with a waxy hydrophobic coating very often. So, fatty acids. Within fatty acids, there are 2 main categories: saturated and unsaturated. In the very basic way, saturated fatty acids are sort of straight molecules without any bends. Unsaturated fatty acids are kinked very often. So in a very simple way, I can present it that this is saturated and this is unsaturated. So saturated fatty acids, therefore, their molecules can be stacked, and unsaturated cannot. That will determine their physical and to some extent chemical properties. So why do we call them? Well, we call them fatty acids because they can be found in fat. But they are carboxylic acids with a very long and importantly unbranched carbon chain. It can be 10, 12, 16, 18 carbons. Because of that long and nonpolar carbon chain, they're not soluble in water. When all bonds within that carbon chain are single, we call these fatty acids saturated. Very much like hydrocarbons, the alkanes, we call them saturated hydrocarbons because they do not contain any double bonds. When there is a double bond, one or more, those fatty acids are called unsaturated. So these are some examples of saturated fatty acids. What I'm going to highlight is the correlation between the number of carbons and the melting point. Lauric acid, you know, coconut oil, which is not like, okay, it's oil, but it's really solid. Melting point is 44. Myristic in the nutmeg, 55. Palmitic, 16 carbons, 63. Stearic, even more, 69, animal fat. Okay? So, quick question, just kind of connecting real life experience. Out of this list, if I would ask you, replace stearic acid with the closest possible relative, what would you choose out of that list? Based on the similarity of properties. It's a stupid question. It's a simple question. What do you think? If stearic has 18, what is the closest to it by the number of carbons? Palmitic. So, stearic acid is found in animal fat, including the fat in milk. In sometimes manufacturers that are not adhering to standards may replace animal fat like butter with a palm oil in products. It's totally safe, but it reduces the quality. Okay? Now, if fatty acids contain one double bond, we call them monounsaturated. Now, if you will compare palmitic acid on the previous screen with a melting point of 63 Celsius, and palmitoleic acid, same number of carbons, one double bond, 0, it drops 63 degrees Celsius. For oleic acid, which contains 18 carbons, just like stearic, the drop in the melting point, 55 degrees, from 69 to 14, if you add single double bond. And then you have polyunsaturated fatty acids. For example, linoleic acid contains 2 double bonds. Linolenic acid, 3. And arachidonic acid, 4. Look at the melting points. We're talking about pure acid, okay? Pure compound. So, -5 for 18 carbons in linoleic, -11 in linolenic. The more double bonds you have with the same number of carbons, the lower the melting point. Check this out. Let's go back to stearic. Look at stearic acid. Melting point, 69. Double bonds, 0. Now look at oleic acid. Double bonds, 1. Same number of carbons, 18. Melting point is 14, much lower. And then these guys. Now, sorry, this is the typo. I just wanted to make sure that we're all on the same page. This is the typo. It's not 2, it's 3. So when you add more and more double bonds, you reduce the melting temperature of this fatty acid. Does that make sense? Now, every progress is a progress. It's good. I really hope that we can finish that on Wednesday and start something else. Okay? So our previous conversation concluded, just a reminder, we were talking about the fatty acids. Again, as a reminder, the fatty acid contains a carboxylic group and a long chain that belongs to some kind of a hydrocarbon. This chain may contain only single bonds between carbons, which means that such fatty acid is saturated. or it may contain double bonds, which means it is unsaturated. Number of double bonds will determine whether it is mono, one, or poly, several double bonds, polyunsaturated. The reason why we focus so much on the unsaturated fatty acids is that they can exist in the cis or trans, as cis or trans isomers. Just a quick reminder, the cis isomer is when two hydrogens are on one side of the double bond, two opposite hydrogens and two substituents are on the other. So in this case, what you see on the left is the cis oleic acid. And you see that this molecule actually is kinked. On the right, it is trans oleic acid. So hydrogens are located on the opposite sides of the double bond. And this molecule is actually linear straight. So the naturally occurring fatty acids contain cis double bonds. Trans double bonds in the naturally occurring fatty acids are extremely rare. So humans cannot synthesize several fatty acids and have to get them with food. Such fatty acids are called essential fatty acids. Among essential fatty acids are linoleic, linolenic, and arachidonic. All these three fatty acids are unsaturated. We just looked at them in the previous table: linoleic, linolenic, and arachidonic acid. Now, let's jump to the properties of saturated fatty acids and discuss how their structure determines the physical state. We already noticed that appearance of double bonds, whether it's one or many, in the hydrocarbon tail of a fatty acid significantly decreases its melting point, which means that saturated fatty acid have high melting point and are solid at the room temperature. The reason for that is that these tails that contain only single bonds between the carbons are held together by strong dispersion forces, because these long tails are very easy to align. This almost perfect stacking of the molecules and the fact that this stacking contributes to the formation of the strong nonpolar dispersion forces interactions explains why saturated acids are solid at the room temperature. So here's an example of a stearic acid, which contains 18 carbons and no double bonds. You can see how these molecules are stacked, almost like, the Pringles in the tub. On the other hand, oleic acid, with a melting point significantly lower than one for stearic, stearic has 69 and oleic has 14, okay, contains one double bond. Okay, so it means that the molecules of these kinked angled molecules of oleic acid cannot form reliable cannot form dispersion forces of reliable strength, and therefore it's liquid at the room temperature. Pretty much those molecules cannot align, just like chips that you get out of the bag. So we're going to go back to the reason why we want to talk about, trans double bonds, cis double bonds, and the fact that straight molecules can form this really strong interactions between each other. But now we're going to mention prostaglandins. So prostaglandins are chemicals that are produced by human cells, and they're derived ultimately from arachidonic acid, which is polyunsaturated. I believe there are 4 double bonds, and the acid molecule contains 20 carbon atoms. Okay, so arachidonic acid gets modified to form this cyclopentane ring, and then different substituents at the cyclopentane ring will give this prostaglandins different properties. So for instance, prostaglandin F2 is one of the regulators of the inflammation. As a matter of fact, prostaglandins play a role in inflammatory responses, in pain, in regulation of your clotting responses, platelet responses, as they mentioned here, the relaxation and contraction of the uterine smooth muscle. So basically, prostaglandins are responsible for the onset of labor contractions. And this scheme here, I wouldn't call it a reaction, actually shows how drugs such as ibuprofen, Tylenol, aspirin, naproxen, what they do to reduce pain and fever. There is an enzyme, well, actually several enzymes, called cyclooxygenases that facilitates the conversion of arachidonic acid into prostaglandins. So far good. So this non-steroid anti-inflammatory drugs that we just listed, they block those enzymes. Okay. Now, I believe most of you are hoping to get into the medical field, correct? So one of the things that a physician will tell a patient after prescribing, say, Tylenol or aspirin to a less extent, or ibuprofen, take it, let's say you get ibuprofen for pain. Physician will tell you, take so many doses for 5 days and then stop. Among functions of prostaglandins is the regulation of the mucus production in your stomach. If you take non-steroidal anti-inflammatory drugs long enough, they start messing with the production of mucus. Thinner mucus means that acid in the stomach can now reach the cells, and people develop gastritis. It's an absolutely normal and common side effect of non-steroidal anti-inflammatory drugs. Now, these are some of the NSAIDs that we use, okay? Aspirin, and they all have slightly different effects because they may target more efficiently slightly different enzymes. For instance, aspirin, while can be taken as the fever reducer and pain reliever, now is used for the most part to prevent clotting, prevent strokes and heart attacks, because it inhibits the enzyme that synthesizes one of the prostaglandins called thromboxane A, which reduces platelet activation. Ibuprofen and naproxen are used mostly as painkillers, and they reduce inflammation as well, for the most part inflammation, while Tylenol, acetaminophen, that for some reason is excluded from the picture, acetaminophen is very good at blocking pain sensations. Now, some of the things here. So ketoprofen is sort of a very modified version of ibuprofen. To my knowledge, ketoprofen is not the over-the-counter medication in the United States, and I'm not even sure if it's allowed because side effects are much more dramatic. Okay? Now, why do we care so much about those unsaturated fatty acids? So it turns out that the reason, first of all, the reason why oils, like vegetable oils, are liquid is because they contain mostly unsaturated fats. Okay, we're going to talk about the benefits to the health, and I will comment on that. Another place where you can find this is fish. Okay, and we're going to do a little exercise in terms of why fish. Okay, so those fatty acids are sometimes classified based on the position of the first double bond if you count atoms from the very end of the hydrocarbon tail. So check this out. Linoleic acid as well as arachidonic acid are considered to be omega-6 acids. So why do we call them this way? Are you more or less familiar with the Greek alphabet or no? It's totally fine to say no. Anyone knows the very last letter of the Greek alphabet? We actually have an expression in English, from alpha to omega. Omega is the last letter. So the last carbon is sometimes called, it's a terrible representation of omega. I'm going to try my best. That's omega, the Greek letter, okay? So that's omega carbon. And then you start counting. So omega carbon is 1, and then 2, 3, 4, 5, 6, and this is where you find the first double bond. Therefore, the name omega-6. It shows you where the first double bond occurs. Now, so among animals, high levels of omega-3, cis omega-3 fatty acids can be found in fish. Okay, so fatty acids that are isolated from fish are omega-3. Okay, you can see that here. This is the terminal carbon, the omega carbon. And then you count 1, 2, 3 until you run into the first double bond. Are we doing okay so far? So remember how we talked about the melting points of fatty acids, remember? Let me scroll back. Or better this. So remember how saturated fatty acids form this nice stacks of molecules, and therefore solid at the room temperature. Clear? And how unsaturated fatty acids, due to the cis double bond, cannot do that. They're all like kinked and can't align properly, okay? Clear? So they remain liquid. Does that make sense? Because molecules cannot interact strongly with each other because of their shape. We're good? So it explains, right, why vegetable oils are liquid. But last time I checked, fish isn't. Fish isn't liquid fish, right? So which fish contains highest levels of omega-3 fatty acids? Cold water fish. If you will take an oil, like cooking oil, and put it outside, and it's like super cold outside, may it solidify eventually? Sure, why not? If fatty acids that compose that oil will cross the melting point and it will become solid, right? So in the cold water, those omega-3 fatty acids are essential for the functioning of the fish membranes, cellular membranes, so they don't become super solid. Those fatty acids with a low melting point, they kind of allow the membranes to maintain the partial fluidity. If that would be a saturated fatty acid, no. And warm water fish doesn't need that. Am I making sense? So fish that can survive mostly in warm water. Cold water fish, take herring, like Northern Atlantic herring. It's pretty cold out there. If you take that herring and put it in an Ohio pond in the middle of July, it's going to die. For multiple reasons, but temperature is one of them. Okay? So anyway, what's the buzz? It's been shown that omega-3 fatty acids, I would not make that statement, but I would kind of support that. So consumption of omega-3 fatty acids was linked in mouse model to the reduced clotting potential of platelets, which is important for people who have diseases like atrial fibrillation or diabetes mellitus, atherosclerotic disease, anything that increases the clotting potential of platelets. Are you with me? Now, studies on humans, complicated. Okay? So I studied obesity for 5 years. I can tell you this. Studies that show that consumption of omega-3 saturated fatty acids as supplements, you can buy them in any pharmacy, that it makes a difference on top of the drugs that people with those conditions take. Those studies are inconclusive. Am I making sense? We don't have enough data showing that the benefit of omega-3 fatty acid supplements. We don't know. It doesn't hurt though. However, there is an ample evidence that increased proportion of oils, i.e. unsaturated fatty acids, in the diet does decrease the risk of developing cardiovascular disease later in life. In other words, when you choose dressing for the salad, choose oil, okay? Rather than, what will be Caesar word. Okay. Little comment from the person who really studied that. You know how everybody touts that olive oil is like magical? It isn't. They're all good. Like, if you like the taste of the olive oil, fine. From the health perspective, olive, canola, vegetable, avocado, all fine. Sunflower, yeah, they're all good. Okay? As on the salad, for instance. Now we're going to move on to waxes and triglycerides. So waxes cover fruits, leaves, and stems of plants, making them hydrophobic, okay, and also providing the mechanical shield. Basically, waxes are a waterproofing of the surface where they found. So what are they structurally? Those are esters of fatty acids. So there is a saturated fatty acid that forms an ester bond with the long chain alcohol. Does that make sense to you? Yeah, now. Quick question. Remember we were talking about alcohols before, and we mentioned methanol, ethanol, and then propanol, and finally butanol. And we also mentioned that all these molecules, all these alcohols with 1, 2, 3, and 4 carbons can mix with water. What happens to that property, ability to mix with water, as the number of carbons increases? Can an alcohol with, let's say, 10 carbons mix with water? In an alcohol, this group, OH group, polar or non-polar? Remember how we determine polarity of the bonds, electronegativity. Oxygen has electronegativity of 3.5, carbon 2.4, hydrogen 2.1. So polar or non-polar? The difference is more than 0.4 in electronegativities. What do we classify it, folks? If the difference in polar, yeah. So this is the polar part. Remember, bonds between carbons are nonpolar. So the longer the chain, the more nonpolar that molecule becomes. Does it make sense? So here you have a long chain of carbons in the fatty acid and the long chain of carbons in the alcohol. Altogether, that makes molecules of wax very hydrophobic. Okay, and that, how it protects places like leaves and fur from water. Am I making sense? So these are just some examples of different waxes with the formulas. I'm not going to talk about the source and the uses. I want to talk about the number of carbons. So look, this is the number of carbons, total of 16 in the acid and 30 carbons in the alcohol. 26 in the fatty acid, 30 in the alcohol residue, 20 in the acid, 20 in the alcohol. So it illustrates the point that each chain is pretty long. Now, when we store energy in the form of fat, we don't store it as a fatty acid per se. We store it as esters, okay? So-called triacylglycerols, okay? Or sometimes we call them triglycerides. Glycerol is the alcohol with 3 OH groups, which can form ester bonds with fatty acids. And when we name those, we change glycerol to glycerol, just like we change methanol to methyl, ethanol to methanol to methylate, and ethanol to ethylate. So here's an example. This is the triglyceride molecule that is formed by a glycerol and 3 molecules of the stearic acid. So the term for this will be glycerol, because glycerol loses hydrogen. Tri, because there are 3 residues, stearate. You can see that hydrogen and OH groups form molecules of water, and glycerol and fatty acids are now connected by the ester bonds. Okay. Questions? Now, this triacylglycerols form human fat, energy storage, okay? So, when you break down a molecule of triacylglycerol, an enormous amount of energy is released. Fats are much more effective in terms of energy storage compared to glucose. Does that make sense? They can be tightly packaged, and they will be deposited in adipose cells as fat and can be used later. So, for instance, are you familiar? Did we mention the fattest bear contest? Did I ever know? So, I think it's a Katmai National Park in Alaska. They run, and it's a cute contest. They run the fattest bear contest. They film bears in a park, and they have names for them. And they usually name them after like famous people. And then you can visit a website and vote for the bear that you think is the fattest. And then there is a winner. There is absolutely there's no prize. You get nothing from it except for pictures of grizzly bears. And boy, do they get fat. Like seriously fat. Because they consume high caloric foods. When I was a kid, we had a country house, and we would go to the forest and I would forage collecting nuts and berries, and I was told that you have to be very, very cautious, and you have to listen to the noises, because there's another animal that loves berries, and that's a bear. Okay? So they would eat it, they would accumulate insane amount of fat, and then they will go to hibernation, and they will hibernate for several months. Metabolism will slow down, and that means that they have enough fat left to get them through the winter. Okay? Same happens to other hibernating animals, just like groundhog. Okay? So, is it possible for humans? There was a case of a gentleman, I don't remember exactly his starting weight, but it was something around 600 pounds. And he did not eat anything for a year, allegedly. And lost, I mean, as many stories, you can find this in current time, it may be horribly embellished. But you probably, if you can drink water, sure. Okay? Does that make sense? Now, I can tell you another animal that uses fat for slightly different purposes. The humps on camels contain fat. In camels' fat, and I don't know the biochemical mechanism of it, but in camels, that fat in the hump is the source of water when they cross the desert. Okay? So when we talk about fats and oils, usually we refer to this. Fat is solid at the room temperature. Usually it comes from animal sources, while oil is liquid at the room temperature and usually comes from plant sources. Now, in this case, palm oil and coconut oil are the worst examples of the sources of oils. Have you ever seen coconut oil?
Yes.
Is it liquid?
Yes.
No, it's solid. Like when you buy coconut oil, like cosmetic coconut oil, it's solid at room temperature. You have different experience? I'm just curious.
I used to use for the hairs coconut oil.
Interesting.
That's liquid.
Okay, fair enough. Because the melting point, I think, is pretty high for it being. I need to check. I'm really curious. Palm oil is added to food to replace animal fat. Even that. Okay. So I would use more like avocado oil or olive oil because they liquid at room temperature. So different oils contain different proportion of mono versus polyunsaturated fatty acids. So olive and peanut oil, mostly monounsaturated. These, I'm not going to read it for you. So basically, they have a lot of polyunsaturated. And here's the thing. Palm and coconut oil are solids at the room temperature. Okay? They are. Mostly saturated fatty acids. Okay? We already discussed this. We kind of going in circles here with these notes. But saturated fatty acids have higher melting points because of the packing of these long saturated chains. And they found in animal fats and these two plant oils. Unsaturated fatty acids, because they have that bend. See what happens? Those bended tails make it harder for them to stack up, and therefore reduce the interaction between the molecules and reduce the melting point, so they're liquid. So this is a good example of how the percentage of saturated, polyunsaturated, and monounsaturated fatty acids differ between different types of oil. So solid, okay? You see a lot of saturated. Butter, coconut oil, a lot of saturated fatty acids. Now, here you start looking at plant oils. And they, by and large, so orange and yellow bars represent mono and polyunsaturated oil, fatty acids, respectively. Okay? You can see that they contain a fair amount of those unsaturated fatty acids. Now, hear me out. I want to just go on a little tangent about oils and prove to you that olive oil may not be superior. Okay? So humans benefit from both mono and polyunsaturated fatty acids. Do you follow my train of thought? Yeah? So when you start looking at olive oil, okay, what you see is mostly monounsaturated and very little polyunsaturated. Okay, clear? Now, I'm not going to go far. I'm going to go to canola oil. Does it contain less monounsaturated? Sure, but the proportion of very valuable polyunsaturated oils increases. And canola oil is much cheaper. Okay? You start looking at sunflower oil, check it out. A lot of polyunsaturated fatty acids. It's even better. Okay? Does that make sense? And I don't know, anyone uses sunflower oil? No?
I do.
You do? Refined or non-refined? What are you using? Huh?
We made it at home.
Oh, then it's non-refined.
Yeah.
Does it have a very specific smell and
Yeah.
taste? Yeah. So if you decide to try sunflower oil, when I was growing up in Soviet Union, that was it. That was the whole thing. We didn't have any other oil. But there are two types, refined and non-refined. Go to Russian, Ukrainian, Polish, I cannot say anything about Arab grocery store or Indian grocery store, but Ukrainian, Russian, Polish, they will have non-refined sunflower oil. Buy a small bottle, try it on your salad. Maybe you will not like the taste, but it does have a very interesting and specific taste. I love it, personally. Okay? You're familiar with sunflower seeds? That tastes like basically like sunflower seeds, which is really cool. Okay. So let's talk about chemical properties of triacylglycerols. So since double bonds in unsaturated fatty acids are not saturated, they can react with hydrogen and produce a single bond. Okay? So for this, oil is heated and hydrogen is bubbled through. Now, here's what happens. Look, you have triolene or glyceryl trioleate, the triglyceride or triacylglycerol, which contains 3 residues of monounsaturated oleic acid. You bubble hydrogen through, and those double bonds turn into single bonds, and now you have glyceryl tristearate. You effectively, and remember, double bonds, do they reduce or increase the melting point? Double bonds, do they make them liquid or solid? this. The liquid, the oils, do they have more saturated or unsaturated fatty acids? No. Liquid. Look at this. Saturated is blue. So very little saturated, a lot of unsaturated, right? Now, solid ones have a lot of saturated fat. So you effectively turning molecules with unsaturated liquid to saturated state. Okay? Now, this chemistry, what practical value does it have? What is cheaper to produce? Plant oils or butter? Think about the economics of the process.
I think plant oil.
Okay, of course, plant oil is cheaper. Because you can, like, plants require much less care compared to a farm animal such as a cow, right? Cows grow for a long time before they get into the, industrial milk production. Plants are quick. You have like a few months turnaround, pretty much. Am I making sense? Collection's fairly easy. So overall, plant oils are cheaper. You with me? The only problem with gastronomical use of them, you can't spread them on a bread. What if we hydrogenate those plant oils and turn it into vegetable shortening or margarine? Right? Sounds good? Yeah, sounds awesome. Except for the fact that during that hydrogenation process, some cis double bonds in unsaturated fatty acids do not convert into a single bond, but instead are converted into trans double bonds. Okay? So these trans fats they contribute to the fact that it's solid because it's easier to stack them up. Okay? And the problem is that they not just behave like saturated fatty acids. They behave in a much more sinister fashion. Okay? Consumption of trans fats increase the levels of so-called low-density cholesterol, or LDL, and lower the levels of high-density cholesterol, or HDL. Usually, they have slightly different names. So this is bad cholesterol, and this is good cholesterol. Okay? So this image here illustrates two possible outcomes of the fatty acid hydrogenation. You have a cis double bond, you hydrogenate it, okay, you add two hydrogens. One outcome is you go to a saturated fatty acid, which is fine, and also undesired trans fatty acid. And it's been consistently shown that consumption of trans fatty acids significantly, and I want to emphasize it, significantly increases the level of low-density cholesterol. Okay? The bad one. The one on the left. Now, I want to say a few words in defense of garden variety saturated fatty acids, which are found mostly in animal fat. I want to ask you a question first. Give me an example of several foods that you may eat, or you may not eat, it is fine, but foods that would contain animal fat.
The food?
Which food will contain animal fat? Which animals do we eat?
Meat.
So, perfect. Beef, pork, lamb, right? Something else that we get from those animals.
Is gelatin fat?
Gelatin is a protein. But some other foods that we get from cows and goats, milk. Milk is animal fat. So milk, butter, half and half, all of this is animal fat. Does that make sense? For a very long time in nutrition and dietetics and medicine, there was that idea that consumption of saturated fats increases total and low density cholesterol levels. This has been debunked. Let me explain. If you like a good steak, or a pork chop, or a lamb chop, previously, professional societies would say, well, limit the amount of that meat in your diet because it's bad for cholesterol. You have to survive on fattest pork, pure butter for, I don't know, and heavy whipping cream for several months to actually increase your blood cholesterol through food. Does that make sense? Most cholesterol is produced in the liver, and you really have to jump up your saturated fat consumption if you want to make a dent. In other words, if you like milk, drink milk, whole milk. If you like half and half, drink half and half. Am I making sense? It's fine. So let's take a look at where you can find trans fats in the United States. When I say in the United States, in Europe, they are pretty much banned. Deep fried foods, yeah, okay. Depends, really depends. Now you can't, but if you read the ingredients in a cookie, many cookies contain vegetable shortening like Crisco. That's a trans fat. Okay, if you bake at home, see if you can substitute it with butter. The only reason why commercially cookies are made with vegetable shortening, it's cheaper. Okay. Crackers and chips, depends. Now, most food producers in the United States exclude trans fats from the foods. Margarines, absolutely. Vegetable shortenings, absolutely. Hear me out. Frozen foods, cheap frozen foods. Okay? For example, when the kids were in elementary school, we didn't have much time to cook. So my wife used what she called a male chow. Okay? Meatballs. Frozen meatballs? They taste heavenly. The reason why? They contain a fair amount of trans fat. Trans fat tastes good. A lot of cheap frozen foods, to make them more palatable, trans fat is added. Okay? Does that make sense? It makes them more calorie heavy, and they makes them taste great. So just beware of that. Now, triacylglycerols can also be hydrolyzed in the presence of acid or in the presence of bases. So if they are hydrolyzed in the presence of acid or the enzyme called lipase. The reaction results in a molecule of glycerol and 3 fatty acid molecules. When you do the same reaction but use sodium hydroxide instead, we are dealing with a reaction of saponification. You did this on Monday in the lab. Okay? Remember, you took that olive oil and did your saponification reaction. So instead of forming glycerol and fatty acid, what's formed is glycerol and a salt of a fatty acid. The salts, the sodium salts, fatty acids, result in the formation of solid soaps, and potassium salts of fatty acids is what is used in the liquid soap. So here's the reaction. Check this out. So you have triacylglycerol, glyceryl tripalmitate, which contains the residue of glycerol residue and 3 fatty acid molecules. When you treat it with sodium hydroxide and you heat it up, you get glycerol and sodium palmitate, which is the sodium salt, so solid soap. Okay? Does that make sense? This is what you used on Monday. Now, the next category of lipids is phospholipids. Phospholipids, understanding phospholipids is crucial if you take this class as a prerequisite for A&P. Anyone is taking this class as a prerequisite for A&P now? Huh? Now next semester. No, I'm saying prerequisite. So what I'm saying is this. If you understand how phospholipids work, understanding membranes and transport becomes very easy. So phospholipids consist of glycerol, 2 and not 3 fatty acids like in triacylglycerols. And then the phosphate group, which is connected to so-called amino alcohol. So the bonds that you see here are all ester bonds. Remember our definition of an ester bond. You have a fatty acid, an acid, right? You have an alcohol, and the reaction will produce an ester. Do you follow what I just said? Yeah? So this is acid, and this is alcohol. Am I clear? This part, that makes sense. So phosphate group comes from phosphoric acid. Okay? So we can picture it, and you don't need to know these formulas, but I just want to explain what's going on here. Okay? Actually, I'm going to switch over here. So check this out. So we have phosphoric acid. It reacts on one side with the glycerol. I'm not going to draw the entire molecule, okay? I'm just going to draw a fragment. Okay, there's the bond that looks down, links to the rest of the glycerol protein and to some kind of an amino alcohol, okay? And that is glycerol. So what you get out of this is something that looks like this. There is phosphorus. Now, phosphoric acid plus alcohol gives you an ester bond. Does it make sense? Because it's acid plus alcohol. Glycerol is an alcohol as well, so it also gives you an ester bond. And you have this OH group sticking up. Does that make sense, that explanation? So all bonds that are shown in that image are ester bond. We specifically highlight that the bonds that phosphoric acid forms with glycerol and amino alcohol are not just ester, it's a phosphoester bond. We highlighted it's just not just your garden variety carboxylic acid, but that it is a phosphoric acid. So there are 3 amino alcohols that are found in glycerophospholipids: choline, serine, and ethanol amine. Okay? Now, why do we call them amino alcohol? Let's take a look at the structure. This part contains nitrogen, so that is amino, OH group, alcohol. In serine, amino, alcohol. In ethanol amine, amino, alcohol. So this alcohol group is the one that forms phosphoester bond. Now, you may wonder why those amino groups are charged. Okay? Now, remember very quickly, I will remind you how amines behave in aqueous solutions. So this is the amino group. When it interacts with water, it becomes protonated. I use just a regular amino group, but, you know, choline, same story. Okay? Does that make sense? That happens in the aqueous solutions. So, 2 very interesting glycerophospholipids are lecithin and cephalin. Okay? So lecithin can be seen on the left, cephalin can be seen on the right. So here's why we care so much about phospholipids. Take a look. Fatty acids are nonpolar, and the amino alcohol together with a charged phosphate group, that part is polar. So effectively, these molecules have a polar head and the nonpolar tails. By the way, we'll get there. I want to say a few words about lecithin later. So this is what we just said. The polar part is an amino alcohol and a phosphate. So this polar part very easily interacts with water. Nonpolar region, it readily interacts with anything nonpolar such as lipids. Glycerophospholipids effectively comprise cell membranes and are indispensable for regulating the permeability of those membranes. So when you start looking at the structure of a glycerophospholipid, you can see that when they form, the phosphoesteric bonds and just steric bonds effectively produce two very distinct regions in the molecule. One is nonpolar, we call them tails, and another one is polar, we call them head. And the way to draw it is like this: the head and the tails. Okay? Questions so far? Now, before we get there, I want to highlight how it's important. So my question is, first of all, what is the most common chemical in the human body? Most common molecule in the human body? Any ideas? You definitely know the answer. You know the molecule. It's not complicated. Humans are composed mostly of what?
Cells.
Water. Water. Everything in us screams water. Inside of the cells are aqueous solutions. Outside of the cells are aqueous solutions. Do you follow my train of thought? So, when you want to form a barrier between two compartments, outside and inside of the cell, you want the surface of your cell to be hydrophilic. So, you form a membrane in which hydrophobic heads are directed to either outside or inside of the cell, okay? And the hydrophobic tails are sort of hidden inside the membrane. We call it phospholipid bilayer, okay? Are we good? So the molecules that contain a polar head and a polar part and non-polar part, let's call them this way, we call them amphiphilic. So both polar and non-polar, not hydrophilic or hydrophobic, but amphiphilic. Okay? Now, in some snakes, their venom contains an enzyme called phospholipase, which can break down phospholipids, the ones that form cell membranes in red blood cells. So what do you think is going to happen if the phospholipids that comprise the membrane of red blood cells when they are destroyed, what happens to the cell? This is not a complicated question. Well, yeah, it dies and breaks in pieces. Okay? What is the main component? Like, what is the role of red blood cells? What do they carry in the blood? Oxygen. And they carry it using hemoglobin. And when they break, hemoglobin is released. So, first of all, hemolysis results in hypoxia of your tissues because you don't have red blood cells to carry stuff around, right? But another thing is that it can lead to the kidney, it will lead to the kidney failure. Kidney cannot process hemoglobin properly, and it causes acute kidney toxicity, and kidney failure is like you die. Okay, but like massive hemolysis is even like your blood is not carrying oxygen around. Now, another type of lipids is sphingomyelin. So sphingomyelin contains a compound called sphingosine instead of glycerol, and only one fatty acid. It also contains phosphate and an amino alcohol. So the sphingosine, let's highlight where's what. So this part is sphingosine. Okay? This part is the palmitic acid. Well, I need to add a little bit more to sphingosine. It's also sphingosine. That central part is phosphate. And this is the amino alcohol called choline. Okay? So now let's classify the bonds so we can turn back to the previous page. So this is not an ester. Remember, when the amine and carboxylic acid form a bond, we call it an amide. This is the phosphoester bond, and this is phosphoester bond as well. Okay? So this is what we just said. The amino group of sphingosine forms an amide bond, and hydroxyl group of the sphingosine forms an ester with a phosphate. Okay? And the phosphate forms another phosphoester bond to either choline or ethanol amine. These phospholipids, well, they are phospholipids, but specifically sphingomyelins, very common in white matter, meaning it's in the myelin sheath. Okay? So sphingomyelins are essential for electrically insulating your neurons and increasing the speed of nerve impulses transmission. Okay? Now we're going to switch gears and talk about structurally very different molecules, the steroids, okay, which pretty much all are produced from cholesterol in the liver and other organs that we're talking about, the hormones. So steroids all contain the steroid nucleus. Okay, you can see that there are 6 cyclohexane rings, A, B, and C, and 1 cyclopentane ring, D, and they all are numbered in a specific fashion. You may ask, do we need to memorize the order of numbers in the steroid molecule? The answer is, of course not. So in the in the steroid nucleus, there's a couple more things I want to highlight. This. Since this is a line angle formula, 19 and 18 are carbons of methyl groups. So overall, this nucleus is pretty hydrophobic. So cholesterol is the steroid that's found in the body. It contains a really, really big nonpolar chunk. Okay. And this tiny little hydroxyl group, which is makes it a little bit, just a tad polar. So let's give some context to the statements here. So cholesterol is obtained from food. Yes. About 15% of all cholesterol is obtained from food. Most of it is synthesized in the liver. Remember how I told you before that consumption of cholesterol-rich foods is unlikely to increase your cholesterol levels dramatically if you just eat like milk or eggs. This is why. Most of the cholesterol is still synthesized in the liver. You can barely make a dent. Like, you really need to put yourself into it. It is essential, absolutely, for cell membranes, tissues to regulate hormones and stuff. Clogs arteries when high levels, form a plaque. There's a lot to unpack here. First of all, mostly low density cholesterol or bad cholesterol. So if you consume a bunch of trans fats and your bad cholesterol skyrockets, yeah, you're going to form a plaque and it will clog the artery and it will impair the blood flow, and it's much easier to block it with a clot, and people with atherosclerosis will likely to have a heart attack. Okay? So, again, I bring you seriously. I'm not bragging, but I kind of am bragging. I bring you the evidence-based stuff. So, the total cholesterol in plasma, that parameter is considered to be obsolete in evidence-based medicine for a long time. Okay? I mean, unless your total cholesterol is like 500 or 400, yeah, we have a problem. But if it's elevated above 200, and let's say up to 10, the most important parameter that you need to look at, you need to ask yourself a question. What about HDL to LDL ratio? If you have a lot of high density and very little low density, good for you. It's perfect. Okay? So this statement is, it does lower the overall cholesterol level. Okay, hear me out. First of all, the lowering is pretty marginal, and it's unimportant because serum cholesterol is not really critical. You know how previously, I don't know, maybe your parents told you, my parents definitely did, that you shouldn't eat more than 1 egg a day because it contains a lot of cholesterol. Okay? You can easily change your diet and eat 6 eggs a day, and your cholesterol will be just fine. I mean, presuming that your diet is overall pretty healthy. Like if you polish it with half a pound of bacon covered with melted butter, yeah, it's not good. You know, you will increase your cholesterol levels. But as a part of a normal diet, it's totally fine. Okay? Now, another chemical that is produced from cholesterol are bile salts. Okay, so bile salts, just like phospholipids, so they synthesize from cholesterol. Bile salts are stored in the gallbladder in the form of bile, and they have polar and non-polar regions. So the reason, the meaning of bile salts, the function of bile salts, is to solubilize fat. Let me explain it to you. Imagine I give you half a cup of oil, just, vegetable oil, and ask you to add it to my bottle with water. Okay? Will they mix water and oil? They won't. But now I want to make, the oil gonna exist as like blobs, right? Now I want to break these blobs down. What should I add to solubilize the fat? You all have it in the kitchen. What do you use to clean a fatty skillet?
Soap.
Dish soap, yes. Soap will solubilize because it has a polar and a non-polar regions. Bile salts will work just the same way. They will solubilize fat in your intestines and make it more digestible. Okay? So it says absorption of cholesterol. I told you, chemists aren't allowed to write anything about human physiology, ever. Absorption of all lipids. Okay? Now, this gets even worse. Large amounts of cholesterol accumulate in gallbladder. Well, cholesterol in gallbladder comes from bile salts. Basically, when your bile is being concentrated. Okay? These are gallstones. Gallstones, do you think they are... So, okay, this is a formula of a bile salt, but I will return to this. So that part is pretty polar. There are charges, there's a bunch of oxygens, polar bonds, and whatnot. This, on the other hand, is a nonpolar part. Okay? Now, hear me out. Let's talk about this. I promise it's going to be entertaining. So first of all, if your diet includes a lot of fat, you have to produce a lot of bile. Your liver will produce a lot of bile to solubilize it. Are you with me? And when you stop eating, bile is still produced and it's pumped, well, not pumped, kind of goes into the gallbladder where it sits and gets concentrated. Follow me on this. Let's say your lifestyle is sedentary, so you're not moving around a lot. So that bile will not be sloshed. And when it's concentrated, the chances are bile salts will precipitate together with cholesterol, okay? And form pretty soft gallstones. And these gallstones will probably block the duct that lets the bile out, and your gallbladder will swell and enlarge. It's painful. Okay? It's called cholecystitis. If somebody has gallstones, what is usually done with the gallbladder? They remove it. People cannot store bile. They still can produce it, but they have to be careful when they eat fatty foods. Okay? Now, do you think gallstones are soft or hard?
You said soft.
They soft. They soft because they consist mostly of fat. I mean, not fat, but lipids, cholesterol, right? They actually pretty soft. And finally, the piece of trivia, which I think you're going to like. I want you to just guess the size of the largest gallstone ever removed from a person, single gallstone, from a human being, after which that human being survived and went on to live their miserable lives. Largest gallstone. You can give me a size, you can give me a mass. What do you think? Come on.
2 mm?
Huh?
2 mm?
2 millimeters?
Yeah.
That's like Boring Tuesday. It will go through a duct by itself.
5 centimeters.
Any other ideas? You slightly underestimate humans. You
1
can,
inch?
huh?
1 inch?
I'm not going to torture you anymore. The largest gallstone was removed from a British woman who was like pretty obese. It weighed 14 pounds and was the size of a watermelon.
How big is the gallbladder?
Oh, it stretched. It stretched all right. Okay? It's absolutely real Guinness Book of World Records.
And this person survived.
Mhm.
That's great.
Obviously, she lost her gallbladder, but she survived, yeah. Okay? Yeah, it's pretty insane. Human body is very, very resilient. Okay, now, McKenna, you seem befuddled.
Like, they found it at 14 pounds? Like, why did
She went to a hospital
why
at
did
14.
she get it removed before then? She didn't know there was
That's a great question. On the tangent, I'm going to tell you something when we're done, okay? Because it's absolutely tangential. I have a very pessimistic view of humans in general. I'll explain why. So the problem with lipids is that they have to be transported in the blood. What is the main component of blood? Chemical. Main blood consists mostly of what?
Water?
Yes. Lipids cannot be dissolved in water. Here's the problem, right? You can transport carbohydrates such as glucose or something, you know. You can transport carbohydrates or amino acids, but not fat. Okay? So, what do? We combine lipids with water-soluble glycerophospholipids and proteins. Altogether, these three kinds of molecules form complexes called lipoproteins. And the esters of cholesterol that are formed by fatty acid and cholesterol is the way cholesterol exists in the blood. So now let's take a very, very careful look at a lipoprotein. So in the core of the lipoprotein are the esters of cholesterol and triacylglycerols. So triacylglycerols, or fats, right, are they hydrophobic or hydrophilic? Fats. Polar or nonpolar? Can you dissolve fat in water?
No.
No. So they are hydrophobic, right? Now, the esters of cholesterol are also very hydrophobic, right? Because check this out. The cholesterol is hydrophobic, nonpolar. And fatty acid is nonpolar. So trying to mix those compounds with water in your blood is not going to happen. It's not, So we need to cover those hydrophobes into something hydrophilic. It's kind of like a Trojan horse, okay? So the surface of phospholipid is polar because there are, phospholipids with the polar head and nonpolar tails. So polar heads face blood, okay? Does that make sense? Hang on a second. Okay, let me see if I can make it work again. I think I can. Okay, so polar heads, it shifted, I'm sorry, that. So polar heads interact with water, non-polar tails interact with inner core. Okay? Does that make sense to you? These polar surface shields those fats from blood effectively, okay? And there are 4 main types of lipoproteins. Now, bear with, here's the question. If you take a fat and like oil, okay, and you drop it in the water, is it going to sink or is it going to float? Okay, so these are 4 different types of lipoproteins. Okay. Chylomicrons, VLDL, LDL, and HDL. So what I want you to take a look is the percentage of lipids. You see how the percentage of triacylglycerols goes down? Can you see that? So effectively, when you go from chylomicrons to HDL, overall percentage of triglycerides goes down, but the levels of protein dramatically increase. So here's my question. If you take a piece of beef and throw it in the water, is it going to float or sink? Sink, because protein is denser than water. So you see that the density increases from chylomicrons to high density lipoproteins, therefore the name. Now, the different types of lipoproteins transport fats to the tissues from the liver or the other way. So LDL, specifically low and very low density lipoproteins, so these 2 guys transport from the liver to tissues. HDL, on the other hand, transports from tissues to the liver. Okay? So why this is important? What do you use fat in your body for?
Energy.
So now, look, I'm gonna give you a very simple rendition of this. So you have liver, you have tissues. From left to right, LDL, VLDL. From right to left, HDL. If you are physically active, do you use more energy? Yes. Which means you will utilize more of the content of these lipoproteins. Am I clear? Which means you're going to have much less of this because you're going to be using them like crazy, and much more of that. In other words, it's been shown that physical activity increases the levels of the good cholesterol, high density, and reduces the levels of bad cholesterol, low density. And this, on top of that, your cardiovascular system will start forming plaques using, quote unquote, using LDL and VLDL, but not HDL. So HDL does not contribute to the risk of having atherosclerosis. Am I clear? Okay. Steroid hormones produced from cholesterol include male sex hormones, female sex hormones, and mineralo and glucocorticoids. Mineralocorticoids such as aldosterone and glucocorticoids such as cortisol, which is responsible for the stress responses. Now, these are some different steroid hormones. Those are naturally produced. Testosterone is produced in testes, not surprising. Estradiol is produced in ovaries as well as progesterone. This is the synthetic analog of a progesterone. Now, why do we talk about this? Anabolic steroids, okay, used illegally to increase muscle mass. Okay, I have a question for you. Can you get prescribed a testosterone supplement in the United States legally? Yes. You can actually do it online. You can do it online. There are physicians that work like you. There are some ways to get testosterone supplements, obviously, to get jacked, right? Now, the word illegally here, I don't think it's illegal. You're not going to go to jail. But, you know, if you participate in sports, you can be disqualified. Making sense? Okay? Now, they do have some side effects. Fluid retention, hair growth, well, for some people like me, it's not a side effect. Maybe a good thing. Sleep disturbance, liver damage. But let me tell you something. So when the bodybuilding industry started, people figured out that if you shoot yourself with testosterone, you grow muscles fast, right? In men, testosterone stimulates production of sperm. And when people started using external testosterone, their own testosterone shut down. So when they stopped using it, lo and behold, their testes shrunk and they became infertile. Another interesting consequence of this. In men, testosterone is metabolized in the liver, and one of the products of that metabolism is estrogen. Yeah, it is excreted later. But if you start loading your liver with testosterone from the syringe, your estrogen levels are going to spike as well. One of the side effects, gynecomastia. Those bodybuilders, on top of the muscle, started growing boobs. Okay? Now, the synthetic derivatives of testosterone largely avoid that problem. Okay, still liver damage. Corticosteroids, it's not an endocrinology class, so just generally. So yeah, we have aldosterone, which regulates water balance, and we have cortisone, which does increase blood glucose. It does not stimulate synthesis of glycogen in liver. As a matter of fact, it stimulates the breakdown of glycogen in the liver. These are some adrenal corticosteroids. I'm going to highlight just one. You see prednisone? So cortisol and cortisone both are pretty strongly anti-inflammatory. You use prednisone to fight inflammation, like an eczema cream. We'll use prednisone or its derivative. Okay? Now, the last bit that we're going to chat about is cell membranes, and then we're going to take a break, a well-deserved break. So cell membranes, as we discussed before, separate what's inside of the cell from what's outside. It's a lipid bilayer that consists of two rows of phospholipids. The inner portion is nonpolar. The polar heads form outer and inner surfaces. So, within the membrane, proteins and cholesterol are not fixed to their location, but rather can float around. This is the model of the phospholipid bilayer. Check this out. The green polar heads, okay, and the yellow nonpolar hydrophobic tails form a border. Within the membrane, you can see proteins, cholesterol molecules, and even carbohydrate modifications. So why do we call it a fluid mosaic? Because while it is a barrier, it's not a solid, a fixed barrier. It contains a fair amount of unsaturated fatty acids that makes those cell membranes fluid-like. Okay? And the role of the proteins in the membrane, for the most part, is communication and transport. They can be receptors, they can be channels. The role of carbohydrates is mostly the recognition by other cells of the body. Okay, now, I have no idea what's going on here. Yes. So, how do molecules cross the membrane? So we have three types of transport. I'm going to expand a little on that. So we have diffusion, which is called passive transport. And then we have what these authors call facilitated transport. So channels or carriers to increase the rate of diffusion. That is not a correct statement, to be honest. I will explain why. And then we have an active transport. Okay? So these are three types of transports. You have diffusion. You see that's the movement of the area with a high concentration to the low concentration. Facilitated transport that uses some kind of a protein. And active transport that moves the molecules from the low to the high concentration. Okay? Now, I think that this is not a perfect classification. I'm going to give you what makes way more sense. So check this out. And that's going to be the last thing, and we're going to take a break. So membrane transport can be divided into passive, which is the same as diffusion, and active. Okay? In passive transport, the particles diffuse from their high to low concentration. Does that make sense? Downhill. Do we need energy for such process? If you want to go, like if you want to roll the ball downhill, no. In the active transport, the particles are moved uphill. Do we need energy?
Yes.
Now, I'm not going to go into the weeds of active transport, but for the passive transport, I want you to understand that there are two types here. Simple diffusion and facilitated diffusion. So simple diffusion is reserved for small nonpolar molecules. And it happens directly via membrane. Facilitated diffusion carries polar or hydrophilic, in other words, molecules. And to do this, remember, the inside of the membrane, the yellow tails here, they are nonpolar. So polar molecules cannot cross the membrane directly, and facilitated diffusion requires channels or carriers. So I want to emphasize, hear me out. Simple facilitated transport is still diffusion because molecules move from high to low concentration. Does that make sense? It just facilitated. So the proteins and carriers, they needed not to increase the rate. They needed to actually allow those molecules to cross the membrane. Are we clear? Okay. So that's the end of the story with lipids.